The general aviation community has long operated under an unspoken agreement: trust the aircraft, trust the manufacturer, trust the certification process. But what happens when that trust is built on structural compromise? The Piper Aircraft Corporation, a name synonymous with training aircraft and personal aviation for over 8 decades, has faced a dark pattern of wing failures that raises fundamental questions about design philosophy, regulatory oversight, and the true cost of accessible aviation. Between 1968 and 1998, the National Transportation Safety Board documented 32 in-flight breakup accidents involving Piper PA-28 and PA-32 series aircraft due to wing spar structural failures. 32 families shattered. 32 investigations that revealed the same haunting conclusion: the wing gave way when it should have held. These weren't isolated incidents scattered randomly across decades. They formed a pattern, a signature failure mode that engineers and accident investigators came to recognize with grim familiarity. The PA-28 Cherokee series, introduced in 1960 as an affordable alternative to Cessna's dominant trainers, revolutionized flight training and personal aviation. Its simple design, reasonable operating costs, and docile handling characteristics made it the aircraft of choice for thousands of flight schools worldwide. The PA-32 Saratoga and Lance models extended this success into the 6-seat market, offering families and small businesses practical transportation. Together, these aircraft types number in the tens of thousands, filling flight schools, flying clubs, and private hangars across the globe. But beneath the familiar cowling and trusted name lay a structural vulnerability that would only reveal itself under specific, often unpredictable conditions. At the heart of the issue lies the lower main wing spar carry-through structure, the critical component that transfers wing loads through the fuselage. In Piper's design philosophy, this structure was manufactured from aluminum alloy, a material choice driven by cost efficiency and manufacturing simplicity. While aluminum offered adequate strength under normal operating conditions, it possessed a fatal weakness: susceptibility to fatigue, cracking, and corrosion, particularly in the lower spar cap area where bending stresses concentrate. The design incorporated a wing spar that, under certification standards of the era, met minimum requirements. But minimum is a word that carries different weight when your family is strapped into the cabin at 8,000 feet. The certification process tested new aircraft, not the 30-year-old trainers that would still be flying decades later, accumulating tens of thousands of landing cycles, weathering in coastal humidity, and experiencing the cumulative effects of hard student landings and turbulent conditions. Engineers familiar with the design have pointed to several contributing factors. The lower spar cap operates in tension during normal flight loads, making it particularly vulnerable to crack initiation and propagation. Water intrusion through aging sealant allowed corrosion to develop in areas difficult to inspect without extensive disassembly. The attachment hardware created stress concentration points where fatigue cracks could nucleate. Perhaps most critically, the inspection protocols established by Piper and approved by the FAA proved inadequate to detect developing cracks before they reached critical length. What makes this structural vulnerability particularly insidious is its invisibility. An aircraft can appear airworthy on the ground, pass standard annual inspections, and show no obvious signs of distress, until the moment catastrophic failure occurs. The crack grows silently beneath the surface, invisible to standard inspection techniques, propagating with each flight cycle until it reaches a critical length where the remaining structure can no longer bear the load. Pilots and owners operated under the reasonable assumption that their aircraft was safe. They followed inspection schedules, performed required maintenance, and trusted that the regulatory system would alert them to any serious safety concern. Meanwhile, the clock ticked down in sparse structures across the fleet. The failure mode was particularly cruel. It typically occurred during high-load conditions, such as maneuvering flight or turbulence, situations where a pilot needs every ounce of structural integrity to recover. When the spar failed, it failed catastrophically and without warning. One moment the aircraft was flying normally. The next, the wing folded, and physics took over with inevitable, fatal consequences. The Federal Aviation Administration's response to the mounting evidence evolved slowly. Initial service bulletins in the 1980s recommended inspections, but didn't mandate them. As more accidents accumulated, the recommendations grew stronger, eventually culminating in airworthiness directives requiring detailed spar inspections at specific intervals. In 2020, the FAA issued AD 2020-26-16, requiring repetitive eddy current inspections of the lower main wing spar cap on certain PA-28 and PA-32 models. This represented the most comprehensive regulatory action to date, but it came more than 50 years after the basic design was certified and decades after the first fatal failures began occurring. The AD acknowledged what many in the aviation community had suspected. The original inspection requirements were insufficient to detect the developing cracks that led to structural failure. Critics argue that the regulatory response demonstrated systemic problems with aviation safety oversight. The FAA operates largely on a reactive model, responding to accidents rather than proactively identifying potential failure modes. The certification process focuses on new aircraft performance, with less emphasis on long-term structural durability. Manufacturers have significant influence over inspection and maintenance requirements for their designs, creating potential conflicts of interest when structural issues emerge. For owners of affected Piper aircraft, the regulatory response created an immediate crisis. Eddy current inspections require specialized equipment and trained technicians. The inspection process involves significant disassembly, driving up labor costs. If cracks are found, the repair or replacement costs can exceed the value of the aircraft itself, particularly for older trainers. Flight schools operating on thin margins faced an impossible choice: invest tens of thousands of dollars per aircraft in compliance with the new inspection requirements, or retire otherwise serviceable trainers from the fleet. Individual owners, many of whom bought their Piper specifically because of its reputation for affordability, suddenly faced maintenance costs that fundamentally altered their ownership economics. Some aircraft were grounded permanently, deemed uneconomical to inspect or repair. Others received the required inspections, only to reveal cracks that necessitated expensive structural repairs. The secondary market for affected models collapsed as potential buyers factored in the inspection requirements and potential structural issues. Behind every statistic, every accident report, and every regulatory action lies a human story. Families boarded these aircraft for weekend getaways, trusting their lives to structures that appeared sound. Student pilots took their first solo flights in aircraft that their instructors assured them were safe. Business travelers scheduled meetings around aircraft availability, never imagining that the wing above their head contained a developing crack that would soon reach critical length. The pilots who survived wing failure incidents described the experience in haunting terms: an unexplained bang, sudden asymmetric flight characteristics, and the terrifying realization that control inputs no longer produced expected results. Those who perished left behind grieving families and unanswered questions about whether their deaths could have been prevented with earlier regulatory action or more aggressive inspection requirements. The Piper wing spar issue illuminates broader challenges facing general aviation. Aircraft designs from the 1960s continue operating decades beyond their original expected service lives, often under standards that modern engineering would consider inadequate. The industry must grapple with uncomfortable questions about aging aircraft inspection requirements, regulatory oversight effectiveness, and manufacturer responsibility for long-term structural integrity. The technical solution is straightforward: enhanced inspections, improved detection methods, and structural reinforcement when necessary. The harder challenge involves systemic reform of how the industry identifies and responds to emerging structural issues before they become fatal statistics. Manufacturers must take a more proactive approach to long-term structural monitoring. Regulatory agencies need better tools for identifying potential safety issues before accidents occur. The aviation community must develop cost-effective inspection techniques that don't make aircraft ownership economically impossible while ensuring structural safety. For current Piper owners and operators, the message is unambiguous. Compliance with inspection requirements isn't optional regulatory overhead. It's the difference between safe operation and catastrophic failure. The wing spar issue remained hidden for decades, but once exposed, it demands immediate attention and appropriate action. The wing snap nightmare serves as a sobering reminder that trust in aviation must be earned through constant vigilance, not assumed based on manufacturer reputation or certification alone. Every flight represents an implicit bargain, proper maintenance and inspection in exchange for structural integrity. When that bargain is honored, general aviation provides remarkable freedom. When compromised through inadequate design, insufficient inspection, or delayed regulatory action, the consequences are written in wreckage and lives lost. The Piper fleet will continue flying, but under enhanced scrutiny and better inspection protocols. Structural integrity isn't guaranteed by brand name. It must be verified, inspected, and maintained throughout an aircraft's operational life. That's the lesson written in 32 accident reports. The question is whether the broader industry will learn from Piper's experience before similar patterns emerge in other aging designs still crowding our skies.